Gonna get started. The announcements that I have are if you submitted an exam regrade and didn't pick it up from me just now, you can still snag it from me at the end of lecture. Or after that, I'm going to give them back out to the TAs so you can get them in your recitation after that. Also, I'm going to finish up Chapter 7 today. So I'm going to set the sapling due date for Monday 9 a.m. next week. And then finally, guys, if you're in a Tuesday afternoon recitation, you guys still have to do the quiz this week. So that'll be on Tuesday afternoon. Okay, any questions about that? Okay, cool. Alrighty, so we are still in Chapter 7. We finished up looking at cyclohexane. We spent a little while looking at smaller rings. And now we're looking at bicyclics and polycyclics. Okay, so things with multiple rings. So I mentioned last time that there's a few different ways for rings to be joined. One is if they're linked like this with just one edge in common, they're fused. If they're in a structure that has sort of multiple different ring bonds sticking out, then they are bridged because they look like something with a bridge connecting the two carbons. Okay, so we got partway into naming these last time, but the way that you want to do it, just to sort of go over that a little bit more in depth, is identify the bridgehead carbons. So in other words, atoms that are holding together, sort of involved in more than one ring at a time. So for instance, this one here is involved in multiple different rings. This one here is involved in multiple different rings. The same for here and here. It's the atoms holding the whole deal together, basically. Then what we want to do is count the routes between those two bridgehead carbons. So in this case, we have the option of going around the left path, which involves passing through 1, 2, 3, 4 atoms. We could go along the right path, which also involves passing through 1, 2, 3, 4 atoms. Or we could go along the middle path, which is 0 atoms. Or if we do it for this molecule down here, we could go either left route is 1, 2, right route is 1, 2, and the top route is also 1, 2. Okay, so you'll notice that's actually sort of an easy way to tell if you're not clear between fused and bridged. Fused means that there's a direct connection, like a bond directly holding the two bridgeheads together. So if it's fused, your shortest route should always be 0 carbons or 0 atoms. Okay, so then what we're going to name it as is how many total carbons in the whole deal. So in this case, it's going to be 10 if you count them. So we're going to name it as some sort of decane derivative. We're going to call it a bicyclodecane, but we got to include some information about exactly how those two rings are put together. So we're going to call this bicyclo, and then in the numbers, we're going to put the distances of the 4 routes separated by dots in descending order. So this would be bicyclo 4.4.0 decane. This one has a total of 1, 2, 3, 4, 5, 6, 7, 8 carbons. So we'd name it as bicyclo something octane. And again, we're going to list it by the 3 different routes in descending order separated by dots. So 2.2.2, bicyclo 2.2.2 octane. Okay, so you can actually do some pretty easy error checking on this, because note that, for example, in this bottom one, I'm counting all 3 of the routes holding the 2 bridgehead carbons together. So I got 2 carbons here, 2 carbons here, 2 carbons here. And then I've also got the 2 atoms that are the bridgeheads themselves. So in the whole structure, I should have a total of 2 plus 2 plus 2 plus the 2 bridgeheads gives me 8 total carbons. So I can double check that, yeah, this should be an octane actually. Same thing up here. I should have a total of 4 plus 4 plus 0 plus the 2 bridgeheads gives me 10. So I should be naming this as a decane. So your numbers should add up to 2 less than whatever the parent is.
Is there a should that always be?
Yep, descending order always, yep. Mm-hmm. Okay. Okay, so any questions about these two systems, which are really honestly the same system? Okay, cool. So fused and bridged get treated pretty much the same. Spiro is kind of the weird one out because it doesn't have two bridge heads, it just has the one central atom. So say we're looking at this thing. So we don't have two separate bridge heads. We can't look at the routes between them, but we can look at if we start on the central atom and we make one loop that leads us back to the central atom and we make the other loop that also leads us back to the central atom, how long are each of those paths? So here we could go, say, 1, 2, 3, 4, and then back to the central atom. Or we could go 1, 2, 3, 4, and back to the central atom. So I'm going to call this one, I'm not going to call it bicyclo because if you remember from last lecture, spiro compounds like this are not considered true bicyclics, and bicyclo doesn't get to be part of their name. But we are going to call this spiro, and then we're going to have square brackets with just two numbers in there for the two routes. So spiro 4.4, and then because it's 9 atoms total, it's a nonane. Okay, so in this case we can do some error checking. We've got the two routes, which is 4 atoms each, and then the one central atom. So if we add up 4 plus the one central atom, we should get to 9, which is also how many total carbons we have. Okay, so any questions about that? Okay, cool. So a little bit more about the geometry of these guys. So fused rings can actually join in different ways. Stereochemically. So if we're looking at not just the connectivity, like we were up here when we were naming, if we're actually looking at what direction things are pointing, like the stereochemistry of them. Let's go back a little bit to cyclohexane because, again, we spent the most time looking at conformations and stereochemistry there. Okay. So here's a cyclohexane stuck to another cyclohexane. And we know from naming up here that this is a total of 10 carbons. It's a bicyclodecane. The nickname that gets stuck on this thing is actually decalin. And there's actually two different ways you can do this. One is, so we know that these two bridgehead carbons each have to have one H coming off of them, right, to get a full octet. But to have tetrahedral geometry on there, we got to have either bold or dashed on those H's. So one option is that we have the two H's trans to each other, so one bold and one dashed. And predictably, this one's called transdecalin. The other option is that we make those two bridgehead atoms, the bridgehead H's, cis to each other. So we could call this one, again, same connectivity, just different spatial orientation. This one's going to be cisdecalin because the two H's are cis to each other. And remember that for showing tetrahedral geometry, it is okay to show 3 bonds as sort of like in plane, and then the fourth one either coming out towards you directly or going away from you directly. It's not exactly tetrahedral. It's not exactly accurate for tetrahedral geometry just because the 3 that are shown in plane should be like going slightly away from you in this case, but people tend to show like multiple ring structures, and especially like everything in plane just because it makes it a lot simpler and easier to keep track of. A question?
Why is it called decalene?
I don't know, probably just some historical reason where people figured out it had 10 carbons and they're like, let's throw some name on there. There's probably a story behind it, but I don't know, sorry. Yeah.
Does the name correspond to older the structure?
Yeah, so it's a non-systematic kind of older name. Yeah. Okay, other questions about this one? Okay, so we're doing 6-membered rings. Let's take a look at how this looks if we try to translate it into chairs. Okay, so let's do, all right, so we want the H here to be going up. Let's try to do this as, all right, so I'm going to draw a chair that starts out tilted up to the left. All right, so I'm going to make this my left half of that structure. And I'm going to do an H coming up off of here, which happens to be up axial, and an H coming down in the front, which happens to be down axial. Okay, so what this means is that my two bonds that tie me into the rest of the structure, the other ring, I'm going to draw equatorial here and equatorial there. And I can actually just draw that, I drew that a little bit long, but tie that straight into the next chair structure. All right, so these are actually kind of tricky to draw correctly. I wouldn't ask you to actually do these on an exam, but I may, for example, draw something along these lines and ask you to figure out some information about like what's equatorial, what's axial, something like that would be fair game. Okay, so here's a thing where I've got the H's one up, one down, just like what corresponds to over here being bold and dashed. And then both the bonds to the ring are both equatorial. And if you looked at it the other way, where we made the right ring sort of the one we were focusing on, then you could also say like both bonds leading off into the left ring are also both equatorial coming off of there. So all four of the ring-to-ring connections here are equatorial to each other. I guess let me exchange that both for an all equatorial. Okay, so questions about that? Is anyone having a hard time seeing that? Because model kits are actually super handy here if you're having a hard time. Okay, awesome. So then you might be asking, all right, I drew one chair conformation of this. What's the other one going to look like? So let's try ring flipping this guy. Okay, so I'm going to start out so I drew my first left ring up to the left. Let's do up to the right. Which means that now, okay, so my H over here was coming off of the upmost carbon, or the rightmost carbon, which is pointing up. After a ring flip, it would have to be a down pointing carbon, so I'm going to leave it as the rightmost carbon. So like always, our ring flip converts up pointing ring carbons to down pointing ring carbons. So that means H now is up equatorial. And this other H here has to be down equatorial. Okay. And so that means that my two bonds to the ring coming off of here are now down axial, and coming off of here are up axial. We have a problem because it turns out we just don't have enough reach in the two remaining carbons to actually tie that into a 6-membered ring still. So it's just not going to reach. So what this means is that transdecalin can't actually ring flip at all. It's permanently locked into all equatorial bonds. All right, so transdecalin is just locked in that shape forever. It can't interconvert. Everything is just going to be stuck here. All right, so this is an actual, this is part of something that shows up as a common theme in multiple different molecules. For instance, steroid molecules all have this shape where, so I'm going to go down here a little bit. They have sort of a bunch of trans ring linkages. Where all of the H's are trans to each other at each ring linkage. And so steroids are basically this flat, like permanently locked into one conformation system of rings that are all sort of going off in one direction. There's more to it than that. Actually, yeah, I will draw. The last ring is like a 5-membered ring coming off the side. But they never have the option to chair flip. They're stuck that way forever. Okay, questions about that? Okay, cool. So by contrast, cisdecalin is going to look like, okay, so we start here. If we're showing both the H's up, we could do up axial, up equatorial, which means that oh, actually, hold on. Okay, I'm just trying to make it match up with the notes instead of being rotated from there so I'm not confusing people. Okay, I'll do that instead. Okay, so I'm going to do these in the opposite order from how I drew them in the notes just because that matches the shape of chair I started out with. All right, so, and you can draw it either way, it's just, it's a little bit easier to see what's going on in one shape than the other. Okay, so in this case, what we've got is both H's being up, which means we've got up axial, up equatorial if they're on adjacent carbons. And that means that out of my bonds to the other ring, one's going to be equatorial and one's going to be axial. Okay, and now if I try doing a ring flip. Okay, so I went up and to the left there on the first ring. I'm going to go up and to the right here, which means that got H and H, which are now up axial and up equatorial. And so I can do what actually does look like a chair now that we're viewing it from the right perspective to see that. So the exact angle that you're showing this from determines whether you're actually going to be able to see both rings as chairs or whether one's going to look like a chair and the other's going to look sort of like a top-down view because we've pivoted the whole thing. But it is possible to do a ring flip because in either case you're still going to have one bond to the other ring being one equatorial and one axial. Okay. So this thing is equally stable in both conformations. And neither of them is as stable as over here where everything's equatorial and you don't have to worry about 1,3 diaxial strain. But the trade-off for that is that this has two different states, two different conformations it can be in, and transdecalin just has the one. Alrighty, questions about that? Okay, cool. So one last topic about ring geometry before we go on to the last part of this chapter, which sort of ties the last few chapters together, like alkene geometry, alkene reactions, and stereochemistry and rings. So we're going to spend just a little bit of time first on alkenes and rings. Okay, so there's really two rules that we got to know here. One is that in bridged compounds, note that this doesn't apply to fused. So we can't have sp2 hybridization on a bridgehead if the rings are too small. if all the rings containing it are 7 atoms or fewer. Okay, so it turns out that this just gives too high an angle strain. So you remember we saw a ring strain in 3-membered rings. It's forced to hold a 60-degree angle. That carbon really wants 109.5, and so it was under a lot of strain as a result. Here, we're not just dealing with 109.5 degrees as our desired bond angle. If it's sp2, it wants to be 120 degrees, and there's just not room to allow that. Okay, so this is called Brett's rule. Okay, so as an example of how this might look, let's do our sort of book lying open on its face kind of structure again. All right, so I am never going to see a structure that looks like this. I'm never going to have a double bond to the bridgehead carbon, because if we look at the rings containing this thing, let me shade in what I mean when I say like ring. Okay, so it looks weird from this angle, but this is a ring containing a total of 5 atoms. So 1, 2, 3, 4, 5. So that's too small. Let me redraw the whole thing again. If I look at this ring on the right side, again, I got 1, 2, 3, 4, 5. Or I could try to go for the ring containing the 2 bottom bridges. So like 1, 2, 3, 4, 5, 6. Okay, so 1, 2, 3, 4, 5, 6. So none of the 3 options of doing a closed loop around this molecule is any higher than 6 atoms. So all 3 routes are too small, which means you can never have a double bond to the bridgehead. However, if we do something where we just move the double bond over to a non-bridgehead atom, then we don't care anymore because Brett's rule doesn't apply. We're not looking at hybridization of the bridgehead atoms. So this structure cannot exist. This one is totally fine and is actually a fairly common component of some other systems, of some other larger structures. Okay, or we could just make the largest ring bigger. So, okay, this is going to be tricky to draw. I'm going to draw starting out with like my book lying face down. Maybe I'll do this, and then I'm going to erase the 2 end bits and just do like a V pointing upwards. Okay, so now my largest ring is 1, 2, 3, 4, 5, 6, 7, 8. So that's greater than 7, so now I'm okay to have a double bond to my bridgehead. Okay, so questions about that? Mm-hmm.
So it doesn't need to be all the rings have to be more than 7. It needs to be
Yeah, because it's just the largest ring is going to sort of stretch out of shape a little bit to accommodate the large 120-degree bond angle that the sp2 carbon wants there. So it can sort of take up the slack in the molecule even if the other 2 options are kind of small. Mm-hmm.
matter where the double bond is?
No, I mean like it has to be to the bridgehead carbon. And just as a side note, or sorry. Mm-hmm.
Curious, like, does it have to be with the larger
No, so even if it's like on this smaller bridge here, like the bigger ring can still sort of like flex and take up the extra bond angle strain that it needs to. Yeah, and I guess that actually, leads me into another point, which is sp2 is sort of the most common way that you're going to see this because it's a stable double bond structure, but also you may see this come up as like an intermediate. So for example, going back to this shape up the top here, not just double bonds, but also if you ever try to put a carbocation there as an intermediate, that's also sp2. So this would stop this reaction from ever being permissible. Even though it looks like it would be great, like it's tertiary carbocation, right? But Brett's rule says, So if your reaction ever tries to go through that, it's just not going to work at all. Okay, questions about Brett's rule? Okay, cool. So the second rule that we have to know is something that we actually already covered briefly, and that is rings can't contain trans double bonds if they're 7 atoms or fewer. So both of these actually have the same size limit on rings. 7 atoms or fewer means you can't have a transalkene. 7 atoms or fewer in the largest ring also means that you're violating Brett's rule. Okay, so for example, 1, 2, 3, 4, 5, 6. This is not okay, but if we grow the ring to 8 carbons instead, 2, 3, 4, 5, 6, 7, 8. Then this is actually going to work okay. It might not be super happy about existing that way, but it's at least something that you can make as a molecule that's stable enough to take measurements on. Okay. Questions about either of these? Yeah.
So when we're naming rings that are less than 7, can we leave easy out of it?
Yep, yeah, exactly. So in other words, don't include EZ as part of name, but do include EZ as part of the name for these ones. Okay, good question, thanks. Okay, so that's pretty much all I got for ring geometry. Let's move on to the last part of the chapter, which is kind of tying the last month or so of stuff all together. Okay, so stereochemistry of alkene addition reactions. Okay, so we can actually break down the reactions that we saw in chapters 4 and 5 into 3 different categories. When we did them before, we were just looking at regiochemistry, like what adds where, like is it Markovnikov or anti-Markovnikov or what. But now that we've covered stereochemistry also in chapter 6, we can also look at what direction is stuff pointing after it adds. So is it going to add bold or dashed or what? Okay, so it turns out there's 3 options. So first up is called SYN, S-Y-N, addition. And the deal here is that both groups add to the same face at the same time. Okay, so can you guys remember out of the reactions that we covered, which ones happen to have that happen? Like which ones were adding 2 groups onto the molecule at the same exact instant? Yep, hydrogenation, good. Okay, so hydrogenation, if I do something like this, for example, so H2 and palladium on carbon, The two new H's that I'm adding are both going to be bold or they're both going to be dashed. And I don't have a say over how that happens, so I'm going to get both molecules produced as a result. So for example, I could show both new H's being bold, which means that the two other groups that were on there, say the methyl and the ethyl in this case, both get shoved to the other position. So I'm going to suddenly have a methyl that's dashed and an ethyl that's also dashed coming off of there. And the other possibility is my H's could both add to the underface of the molecule, which means they'd both be ended up as dashed bonds. And that means my other two alkyl groups get shoved to the front. So methyl is bold and ethyl is bold. Okay. So another way to describe this kind of reaction is called a concerted addition. That just means both things are getting added at once. So hydrogenation is one example. Can you guys remember another reaction in this category? Okay, I guess that's a little bit of a complicated question because it's not actually the entirety of the reaction that we covered. But if you remember hydroboration oxidation, the oxidation part is not, but the hydroboration is concerted addition. So hydroboration if I take this molecule here, and I'm just going to draw the H explicitly just so it's easier to keep track, and I do BH3, if you guys remember, the H and the boron add at exactly the same instant, so that means that they both have to be adding from the same direction, which means they're going to end up pointing the same direction coming off of the molecule. Okay, so got two options here again. One is we could have new H be bold. Okay, I'm going to elaborate on this in just a second here because it turns out the oxidation step does change things a little bit. We can look at that in a second. Okay, so we got H is bold, BH2 is bold, and that means that the other two groups coming off of those atoms just get forced into whatever the other space is available. So methyl's dashed, and the H that was already on there is dashed. And again, the other possibility is H is dashed and BH2 is dashed, which means that methyl's bold and the original H is also bold. So note that we're still doing anti-Markovnikov style addition. Boron is still going to the less substituted carbon, just now we're adding in another layer of detail there as to which direction it's pointing. Okay, so I mentioned that hydroboration is one example of a syn addition. It turns out that the oxidation step that happens afterwards is going to what's called retain the stereochemistry that we just made. So if boron's bold here, then when you replace it with an oxygen, the oxygen's also going to be bold. So if we do step 2 here as hydrogen peroxide, base, and water, then it's going to be pretty much the same two molecules I drew over there, just with O instead of B. Okay, so quick question. These two molecules, what is their relationship to each other? Enantiomers, diastereomers, identical? Yep, enantiomers. So we're going to look in just a little bit at what sort of relative amounts things are produced in, but it also helps to do a quick check of like what kind of stuff am I making and what relationship does it have to each other. Okay, so this one over here, sorry, just to finish that thought, is going to do the same thing. Oops. So dashed H and dashed OH. and then the two original groups get pushed to bold. Okay, so that's one possibility. I'm just going to erase the board if you guys want to take a minute. Okay, so next up as a possible outcome is the opposite of syn addition, which is called anti-addition. And sort of the key tip-off here in the mechanism is that one group attacks first, and then the other group comes in and attacks from the back face. So the common factor here, at least out of the mechanisms that we've covered so far, is something makes a three-membered ring, and then something else pops that three-membered ring open. Okay. So, few examples are pretty much anything that involves like a halonium ring. So, halogenation or halohydrin formation. And if you want, you can actually show the mechanism for this where bromine is going to do this thing, if you remember. Before we just showed connectivity, but we could just as easily show those bonds becoming bold, and we could say like plus the enantiomer of this where everything is flipped. And then when the attack happens, the Br minus is going to come in from the opposite direction. So if this bromine's bold, this guy's coming in from the back, attacking here, popping the ring open. And this is the very first case that we've seen of what's going to involve sort of inverting the stereochemistry here. Like as this bond breaks, the methyl gets shoved to the front out of the way again. And this newly added bromine ends up sticking off the back of the ring. We're going to see a whole bunch more examples of this in a couple chapters, but for now, this is sort of the first case. Okay, so again, this plus the enantiomer. Okay, so that's one example. And anything that involves bromonium rings. The other is oxymercuration. So we're going to end up with opposite directions for the OH in the HGOAC, and then that plus the enantiomer. Note that I'm only showing the oxymercuration step here, not the reduction. Reduction, it turns out, actually does what's called scrambling the stereochem. So it's going to give sort of random whether the new H that adds on here is going to be bold or dashed. In this case, you can't tell because there's an H on there already, but it's going to give an H sort of pointing in a random direction to replace the mercury. A question?
Is this true for any reduction, like general reduction, or just?
For this one specifically, yeah, and I'm not sure exactly why the mechanism works out that way, but yeah, it doesn't retain stereochem. Okay, so real quick in the time I got left, third possible category is going to be random stereochem. Okay, so this means there's no control, like both groups could be pointed bold, both could be dashed, one bold, one dashed. So I guess actually a better way to phrase this is mixture of syn and anti-addition. So the key sort of mechanistic feature to look out for here is anything that goes through a radical or carbocation, because we know that both of those have sp2 geometry, which means they don't have any chirality at those carbons. So once you make a carbocation, whatever the new group is that's coming in to attack the carbocation could just as well attach to either face. So these give what's called loss of stereochem, or stereochemistry. Okay, so, or in other words, scrambling. Okay, so if we do, let's do anti-Markovnikov just so we can keep track of, like, so we're actually making two asymmetric carbons out of this. Okay, so if we did HBr and peroxides here, we could have bold H and dashed Br, which means we'd get dashed methyl there. Or we could have dashed H and bold Br. Or we could have bold H and bold Br. Or we could have dashed H and dashed Br with a bold methyl. Okay, so there's pretty much no control over what direction stuff's pointing, just because as soon as you have a radical involved, the group that adds to the radical could stick on either face equally well. Okay, so this is one example of random stereochem. Anything that goes through a carbocation, so like acid catalyzed hydration. or just HX addition. Are also going to do the same thing. Okay, so one real quick note in the couple minutes that I got left. So we've got one category that's called anti-addition here. Please be careful. This is not the same as anti-Markovnikov. So for example, I showed hydroboration up here. Hydroboration is anti-Markovnikov, but it's a syn addition. So we're sort of using these labels to discuss two fundamentally different things. Anti and syn refer to the stereochemistry, like what direction stuff's pointing. Anti-Markovnikov and Markovnikov refer to the regiochemistry, like where stuff attaches. Okay, so I didn't quite finish chapter 7. I'll do the last half of a page on Wednesday, and then we'll get into chapter 8.